Okay, last section in chapter 11, 11.5. It's just a summary of the rest of the stuff that we did in chapter 11. So nothing new here. But but at this point, it would probably be good to summarize what we've talked about. So we talked about five new hypothesis tests in this section. And by the way, I'm including 12.3 in my summary of the chapter 5 stuff. So we talked about 5 different hypothesis tests. In each case, the procedure for running the test is always the same. Okay, you state the null and alternative hypotheses, use StatCrunch to get the p-value, right? Make a decision based on the p-value by comparing it to alpha, and then of course write a conclusion. So the real trick to knowing which test statistic and which p-value to compute, which StatCrunch procedures to, not in my math lab, in StatCrunch. So which StatCrunch procedures to follow is to be able to answer 2 questions, right? So what you need to be able to do in order to know which is the correct test to run is you need to be able to answer these 2 questions. First of all, which parameter am I testing? Okay, am I testing proportions, means, or standard deviations? And then the second question you need to be able to answer is, are the samples independent or dependent? Okay, so if you're testing 2 proportions and you have independent samples, this is the test statistic that you would compute. And in StatCrunch, you would go to stat proportion stats to sample. Now, you don't have to compute this test statistic by hand. I'm just putting it on this page just for your information, okay? But this is the test statistic you would compute, and then this is where you would go in StatCrunch, stat proportion stats. We covered that in 11.1. If you're testing 2 proportions and the samples are dependent, okay, that was the topic of 12.3. This is the test statistic you would compute. And this is where you would go in StatCrunch. You go stat, tables, contingency, with summary, and then you run McNemar's test. That's the strange one. Of all of the tests that we've talked about in this chapter, this is definitely the outlier, right? It's kind of the weird one. But the reason that you go to stat, tables, contingency is because the information, in order to run McNemar's test, the information has to be arranged into a contingency table in order for you to run the test. But anyway, so that's if you're testing 2 proportions and the samples are dependent. If you're testing 2 means and the samples are independent, we covered that in 11.3. Here's the test statistic. In StatCrunch, you go to stat t stats to sample. If you're testing 2 means and the samples are dependent, we covered that in 11.2. This is the test statistic you would compute, and we go to stat t stats paired. Okay, so notice how similar these StatCrunch procedures are. You go to 2 sample if the samples are independent. You go to paired if the samples are dependent. Okay, so that's 2 tests for proportions, independent versus dependent. 2 tests for means, independent versus dependent. So that's 4 tests so far. And then the 5th test we talked about was for comparing 2 standard deviations. If the samples are independent, then you're going to go to stat, variant stats to sample. If the samples are dependent, well, we don't have a special test for that, right? So if the samples are dependent, then you would just, I guess, follow these same steps. Okay, so those are the tests that we talked about. Again, what it all boils down to is being able to answer those 2 questions. Which parameter am I testing? Are the samples independent or dependent? Okay, you need to be able to answer those 2 questions in order to run the correct test. So, and then as far as everything else is concerned, like, the interpretation of the p-value and the comparison of the p-value to the level of significance to make your decision, right? All of that logic is the same as it was in chapter 10, okay? So the p-value is the probability that you would get the test statistics that you observed if, in fact, the null hypothesis were true, okay? So if that probability is really small, then it casts doubt on the assumption that the null hypothesis is true, and so you reject the null hypothesis whenever you have a small p-value. Well, how small does the p-value need to be? Well, it needs to be less than alpha, right? Alpha is the probability that you make a type 1 error. And so you need to be more certain than alpha that you're not making a type 1 error, right? So your p-value needs to be smaller than alpha in order for you to safely reject the null hypothesis. We've gone over that logic so much. If you don't remember all the logic, take a look at the 10.5 video again and watch that video again. Make sure that you understand what the p-value means and why we compare it to alpha in order to make our decision. Because these are questions that I would likely ask you on a test. The other thing that I was going to say before we look at a few examples is, again, all of your negative statements go together and all of your positive statements go together, just like they did in chapter 10. So if you decide to reject the null hypothesis, that means there's evidence to support the alternative. And so that's what you would say in your conclusion, right? So your decision would be decision. If alpha is less than, or if the p-value is less than alpha, reject the null hypothesis. And then conclusion, at the alpha equals whatever level of significance, the evidence suggests that, and then restate the alternative hypothesis in words. Okay, so all the positive statements go together. If the p-value is less than alpha, you reject the null hypothesis. You have evidence to support the alternative. All the negative statements go together. If the p-value is not less than alpha, then you do not reject the null hypothesis, and there's not enough evidence to support the alternative. So with that review in mind now, let's do some mixed practice. So we'll answer a few questions doing some mixed practice. And I think that there's a little bit of a mistake here. You're going to have to add a number in here because I forgot to give you the sample size for one of these samples. But anyway, it says, Kumon promotes a method of studying mathematics that it claims develops mathematical ability. In one question on an exam, a random sample of 350 non-Kumon students resulted in 73 getting the correct answer. For the same question, a random sample of 400 Kumon students resulted in 130 getting the correct answer. Are Kumon's claims substantiated? Test at the 0.05 level of significance. Okay, so go ahead and give the video a pause. See if you can set up the null and alternative hypotheses, okay? See if you can answer those two questions that we talked about on page 1. What parameters am I testing? Are the samples independent or dependent? All right, so give the video a pause, see if you can do those things. Okay, now here's my solution. So first of all, I'm going to call the group of non-Kumon students group 1. And then the Kumon students, sorry, I was looking for where it talked about the Kumon students. The Kumon students, I'm going to call that group 2. Okay, so the null hypothesis. Now in this case, what are we testing? There's almost no clue given. Nowhere does it say anything about proportions, means, or standard deviations. So we really have to think about this, use our critical thinking to figure out, well, what parameter would you use to test Kumon's claims? Well, what are Kumon's claims? Kumon claims that their method of studying develops mathematical ability. Well, if that were true, then on this particular question, on this exam, you would expect the Kumon students to get the correct answer more often than the non-Kumon students. So the Kumon students were told 130 out of 400 of them got the correct answer. Well, that kind of gives it away, right? If you're talking about, you know, blank out of blank, then you're talking about a proportion, right? You're talking about a percentage. So we're talking about 130 out of 400 Kumon students got the correct answer, whereas 73 out of 350 non-Kumon students got the correct answer. And we want to see which percentage is better, okay? So we're testing proportions here. We would say the proportion of non-Kumon students who got the correct answer is the same as the proportion of Kumon students who got the correct answer. That's the null hypothesis, right? The null hypothesis is a statement of no change, no effect, no difference. So we're assuming that those proportions are the same, or those percentages are the same. The alternative then, well, we're trying to test Kumon's claims. And Kumon claims that it develops mathematical ability. So if that's true, we would expect the Kumon proportion to be greater than the non-Kumon proportion. So we would expect P2 to be greater than P1. Or in other words, P1 would be less than P2. Okay? Now, before we go to run this test, it might be interesting to look at the sample proportions to kind of get our bearings a little bit. So P1 hat, the non-Kumon students, it says of the 350 non-Kumon students, 73 got the correct answer. So P1 hat, right, 73 out of 350. That's about 0.209, so about 20.9%. And then P2 hat, that's 130, right? 130 of the Kumon students, 130 out of the 400 Kumon students got the correct answer. So say 130 out of 400. And that comes out to 0.325 exactly. So so that proportion is definitely larger than that proportion by quite a bit, actually. In fact, I'd be very surprised if we didn't reject the null hypothesis here. I think we will be rejecting the null hypothesis. But to be sure, we actually have to run the test, right? Now, since we're testing proportions, well, actually, let me back up. Okay, we know that we're testing proportions now, but remember the second question that you need to be able to answer is, are these samples independent or dependent? Now, if they were dependent samples, then the sample sizes would have to be the same, because dependent samples are matched pairs samples, okay? In this case, the sample sizes are not the same. You have 350 non-Kumon students and 400 Kumon students. So you know that the samples cannot be dependent here. But even more importantly, like even more fundamentally than that, if you read through the scenario, let's remind ourselves what it means for two samples to be dependent. Two samples are dependent if, when you collect your first sample, the second sample is automatically determined based on the way that you chose the first sample. Okay, so an example of dependent samples would be like if you wanted to test, I don't know, like if you wanted to test something and you wanted to get a bunch of twins in your study, and you're going to do something to the first twin and something different to the second twin because they're genetically identical, and so you just want to see, you know, if some medication has a different effect than another medication or something like that, right? So you want to get twins in your study. Well, so you go through and you choose all of twin A to be in your first study. That automatically determines who's going to be in your second sample, right? Because you're going to get their twin in the second sample, and their twin is going to be their matched pair. So, so that would be an example of a dependent sampling, and that's not going on here. It's not like they said, well, for every non-Kumon student, their cousin who was a Kumon student was chosen to be in the other sample or something like that, right? That's not what happened. They just randomly selected 350 non-Kumon students, and then they went out and randomly selected 400 Kumon students, okay? So anyway, so these are independent samples for sure. Okay, so when you're testing proportions and the samples are independent, that's when you go to stat, proportion stats, to sample. Okay, and in this case, we don't have the raw data, we have a summary, so we're going to say with summary. Okay, and the summary that we were given is, well, for group 1, the number of successes was 73. Whoops, 73. And the number of observations was 350. For group 2, the number of successes was 130, and the number of observations was 400. Okay, so let's go to StatCrunch now. So it's stat, proportion stats to sample with summary. 73 out of 350. And then we've got 130 out of 400. And we want to run a left-tailed test. Okay, so we hit compute. And yeah, just like our intuition told us, right? We get a really small p-value. So we're definitely going to be rejecting the null hypothesis here. Okay, so our p-value was 0.0002. Okay, since 0.0002 is less than, what was our level? Oh, it was 0.05, right? So since 0.0002 is less than 0.05, we reject the null hypothesis, right? The probability that we would observe these sample proportions if the population proportions were equal is 0.0002. In other words, it's highly unlikely, right? Highly, highly unlikely that we would have gotten these sample proportions if this were a true statement. Well, so that makes us think that probably this isn't a true statement. So we reject it, right? We reject it. Okay. So at the 0.05 level of significance, the evidence suggests that Kuhlmann's claims are substantiated, right? That P1 is less than P2. That the proportion of, or that the proportion of students who got the correct answer, or the proportion of Kuhlmann students who got the correct answer is greater than the proportion of non-Kuhlmann students who got the correct answer. You could say any of those things. Probably the fastest, easiest way to say it would be to say something like, the evidence suggests that Kuhlmann does indeed develop mathematical ability, right? Okay. And that's it for that one. All right, so moving on. Okay. So this one says the following data represent the daily volume in millions of General Electric stock and Pfizer stock on the same 13 randomly selected days in 2010. Let's see if I can make this brighter. Not much. Anyway, determine if the daily volume of GE stock is greater than that of Pfizer. Use the 0.05 level of significance. Okay, go ahead and give the video a pause, see if you can set this up. Okay, here's my solution. So once again, another question that's kind of vague in the sense that they nowhere does it talk about means, proportions, standard deviations, right? It doesn't talk about any of that. And so again, we have to use our critical thinking skills to figure out, well, which of those parameters would we use to determine the daily volume of GE stock or Pfizer stock, right? Which parameter would we use? Well, we're not talking about like volatility or variation or anything like that. And so I think it's pretty safe to say that we're not testing standard deviations here. And we can also rule out proportions, because in order to test proportions, you'd have to say Like you'd have to say something like, on this many days, out of this many days, this particular thing happened. And that's just not the scenario that we're looking at, right? We're looking at, we just have the measurement of their daily volume of stock, and we want to know if, generally speaking, GE has a greater volume than Pfizer. You can see examples of both cases, right? Like here was a day where GE's stock performance was lower than Pfizer's, but here's a day where GE's stock performance was greater than Pfizer's. So we can't do this on a day-by-day basis. We want to know if, on average, the GE stock has a greater volume than the Pfizer stock, right? We want to compare their averages, or in other words, their means. So we're testing means here, okay? I'm going to call the GE group Group 1 and the Pfizer group Group 2. So the null hypothesis is that the means are the same, right? They perform the same on the stock market. They have the same daily volume, right? The alternative is the thing that we're trying to test. We want to see if the daily volume of GE stock is greater than that of Pfizer. So we want to know if GE is bigger than Pfizer, mu1 bigger than mu2. My family just got home, so my kids are gonna start making noise. I apologize, but bear with me. Okay, so this is the test that we want to run. Now, the next thing we need to do is determine whether the samples are independent or dependent. Okay, so for that, let's read through the scenario again. It says, the following data represent the daily volume in millions of GE stock and Pfizer stock on the same 13 randomly selected days in 2010. That phrase right there is very important. It's the same 13 randomly selected days. In other words, the researchers didn't go out and just randomly select 13 GE stock days and then 13 different Pfizer stock days. That's not what they did. They chose 13 GE stock days, and then they looked at the Pfizer stock days on the same 13 days that they chose for GE. Okay? In other words, once they determined the GE sample, they automatically got the Pfizer sample. Okay, so these, so that's dependent sampling. Each one of these ordered pairs are matched pairs, right? This is the GE stock on a certain day, and this is the Pfizer stock on that same day. So they're matched pairs. This is dependent sampling for sure. So this is dependent sampling. Okay, so when you're testing two means and the samples are dependent, that's when you go to stat, t-stats, paired. Okay, so let's go to StatCrunch and do that. Now, right now, we don't have much to go off in terms of building up an intuition because we don't know what the sample means are. Once we do this test in StatCrunch will spit out what the sample means are, so we can look at them then. But for now, we don't really know what the sample means are. You could maybe look at the numbers and kind of try to get some intuition. It does look like on most days, GE is bigger than Pfizer. So there are some exceptions like this day and the first day. But I think generally speaking, GE is bigger than Pfizer. Is there enough of a difference? Well, we have to run the test to find out. Okay, so let's go into StatCrunch and enter that data, or enter those data, I guess I should say. Okay. Oh, goodness gracious. And then Pfizer. Okay, let me double check real quick, make sure that I've got these in there correctly. Okay, the GE looks good. Moving on to the Pfizer. Okay, Pfizer looks good too. All right, so let's run the test now. So it's stat, t-stats, paired. We want to compare GE to Pfizer. And we want a right-tailed test. Okay. And there's our p-value. So another pretty small p-value. So we're definitely rejecting the null hypothesis here. Oh, I lied when I said it would give us the sample means. It doesn't. What it gives us is the sample mean difference. So it says on average, in these particular samples, there was a sample mean difference of 8.65 and some change. I suppose if we wanted the individual sample means, we could get them pretty easily, right? Because we already have the data in here. So I'm just going to go to stat, summary stats columns, and compute the sample means of each of those variables. Yeah, if you look at the sample means, the GE mean is definitely larger than the Pfizer mean by a pretty substantial amount. So so yeah, it makes sense that we're going to be rejecting the null hypothesis. I would say, yeah, I would say GE is greater than Pfizer for sure. Let's write this down. Oh wait, p-value is 0.0058. That's the most important key piece of information. So all right, so p-value 0.0058. Okay, since 0.0058 is less than 0.05, we're going to reject the null. Okay, so at the 0.05 level of significance, the evidence suggests that the daily volume of GE stock is greater than that of Pfizer, right? And I'm just copying and pasting that from here. The daily volume of GE stock is greater than that of Pfizer, right? I don't know if you can hear that, but one of my daughters just got in trouble. I have a feeling my wife's patience is wearing thin with my kids today. It happens, guys. You know, you'll have kids, you'll understand. Anyway, so that's that one. Okay. Moving on. Last question. Okay, so this one says the Gallup organization conducted a survey in which they asked 1,020 adult Americans whether they felt low-income people pay their fair share of taxes. Then they asked whether they felt high-income people paid their fair share of taxes. Is there a significant difference in the proportion of adult Americans who feel high-income people pay their fair share of taxes and the proportion of people who feel low-income people pay their fair share of taxes? Okay. Well, this one's a little more clear, right? It says in several places that we're looking at proportions, right? So go ahead and pause the video, see if you can set this one up. Okay, here's my solution. So we want to, I apologize. We want to compare the proportion of people who feel low-income people pay their fair share to the proportion of people who feel high-income people pay their fair share. Now, we could figure out what those sample proportions are, right? The proportion of people who feel high-income people pay their fair share, that's 73 sorry. So that's 73 out of, well, hold on a sec. So 73 people said that both high income and low income people pay their fair share. 274 people said that high income people don't pay their fair share, but low income people do. 146 people said high income people pay their fair share, but low income people don't. And then 548 said that neither high income nor low income people pay their fair share. Man, and that's the majority of people. That's weird. I think most people, this must be made up, because I think most people probably feel like, oh, we're all paying too much taxes. But anyway, so this is nonsense. I think it's all made up. But anyway, so how would we compute the proportion of people who said that high income people pay their fair share? Well, I suppose we would add up, yeah, we would add up these two numbers. We would add up the proportion, we would add up the number of people who said both low income and high people pay their fair share, plus the number of people who said high income people pay their fair share, but low income people don't. So the total number, I guess we could say, the total number of people who feel high income people pay their fair share is 73 plus 146. That's 219. On the other hand, the total number of people who feel low-income people pay their fair share, that would be the 73 who said both high-end, low-income people pay their fair share, plus the 274 people who said high-income people don't pay their fair share, but low-income people do. So that would be 73 plus 274. That comes out to 317. Okay, so that's quite a difference, right? In this particular survey, 219 people said high-income people pay their fair share, and 317 people said low-income people pay their fair share. And that's a pretty substantial difference, I would say. I'd be surprised if we weren't rejecting the null hypothesis here. But anyway, the null hypothesis is that the proportion of people who say that high and low income people pay their fair share of taxes is the same. The alternative is that, well, we want to know if there's a significant difference. Okay, we're not trying to claim that one is bigger than the other. We just want to know if they're different. Okay, so the alternative hypothesis is that the proportion of people who think high income people pay their fair share is different from the proportion of people who think low income people pay their fair share. So I'm kind of thinking of it like this. Well, okay. Next thing we need to do is determine if these samples are independent or dependent. And in this case, it's kind of a weird question to ask yourself about this particular problem, because it's the same people in both samples. In other words, we're kind of thinking that, like, there was a sample of people to whom question 1 was asked, and then there was another sample of people to whom question 2 was asked. Well, once you chose the people to whom you were going to ask question 1, you automatically got the sample of people to whom you were going to ask question 2. Right? Namely, they're the exact same people, because you're asking each person in the study both questions. So these are matched pairs, right? Where every person is a matched pair with him or herself. So, so anyway, we're considering these to be dependent samples. In reality, it was just one sample, right? It was just a single sample of people, but you asked them two different things. Okay, so dependent sampling here. For when you're testing two proportions and you've got dependent sampling, that's when you go to stat, tables, right? This is the weird one. You go to stat, tables, contingency. Another kind of dead giveaway that you're going to be going to stat, tables, contingency is that you were given a contingency table, right, in the problem. You're going to go to stat, tables, contingency with summary, and then make sure to run McNemar's test. Okay, let's go to StatCrunch and make that happen. Okay, maybe I'll call these rows something different. I'll call them fair share for high income people and not fair share for high income people. And the reason I'm going to do that is because I'm going to label the columns the same way. So fair share, but this is for low income people. And so this way I can distinguish between the labels. Anyway, then we just entered the data that we were given, or not the data, I guess, but the summary statistics that we were given into the contingency table. And then we run the test. So it's stat, tables, contingency with summary. Remember, when it says to select columns, what it's asking you to do is select the columns where there's actual numbers, where there are actual numbers stored. And that's in these two columns of my contingency table. And then when it asks you for the row labels, it's asking you, where are the labels for your horizontal rows? And they're in the variable for column, in my case. And then we want to run McNemar's test. Look at that, really tiny p-value. Again, this goes along with our intuition pretty well. I need to choose better examples maybe, because we rejected the null hypothesis in all three of the examples we looked at in this section. But anyway, that's okay. You've done enough of these by now to know that if your p-value is large, you do not reject the null hypothesis. But in this case, we just so happen to have seen 3 examples where the p-value was small, and so we're rejecting the null hypothesis in these examples. And so anyway, our decision is to reject the null hypothesis. Okay, and then in conclusion, we would say at the 0.05 level of significance, the evidence suggests that that the proportion, sorry, I was trying to think of a quicker way to say it, but I think I'm just going to end up copying and pasting most of this. The proportion of, I'm just going to say people who feel high income people pay their fair share of taxes, and the proportion of people who feel low income people pay their fair share of taxes are different. Okay, the proportion of people who feel maybe I'll just call them high incomes pay their fair share So the evidence suggests that the proportion of people who feel high incomes pay their fair share is different from the proportion who feel low incomes pay their fair share. Isn't the English language something crazy? I mean, look at this, their fair share. I pronounce the vowels the same, their fair share, but they're spelled in 3 different ways in all 3 places. We got to clean English up, you know, make it more phonetic. Anyway, that would be hard to do because different accents pronounce things differently. So unfortunately, we can't really do that at this point. But anyway, that's that. You have a relatively short homework assignment for this section, but it'll be good mixed practice, so don't skip it for sure. All right, that does it.